Today we're going to be talking about something called the mean value theorem. And essentially the mean value theorem basically says this. If you have a point on the curve, let's just say this is point A and this is point B, and you draw a line that connects point A with point B, and you calculate the slope using the y2 minus y1 over x2 minus x1, algebra 1, there must exist some point C that is located between A and B such that when you find the derivative of the blue curve, let's just say that's f of x, when you find the derivative, the function's derivative must have the same value as the slope between A and B. So essentially, you get this basic equation. F prime of C, essentially you're going to set the derivative of the function, the blue curve, equal to the slope between A and B, f of B minus f of A over B minus A. Now, in order to use the mean value theorem, two things have to be true. It has to be continuous, and it has to be differentiable at all points in the interior between A and B. Different than the extreme value theorem. Extreme value theorem just had to be continuous, but it did not have to be differentiable. Here, it actually does. Now, Rolle's theorem is just a version of the mean value theorem. Here's what Rolle's theorem says. If you have point A and point B, and they are directly across from one another, meaning the line that I draw, let me draw it in here, the line that I draw to connect them is a horizontal line. Well, if I find the slope between A and B, that's just 0. So there must exist some point C between A and B where the function also has a derivative of 0. So that's what the Rolle's theorem says, and that's what mean value theorem says. So let's see how this works on a few problems. Explain why each of the following functions fails to satisfy the conditions of the mean value theorem. Remember, it has to be continuous and it has to be differentiable at all points in this region. So, square root of x squared. Well, if you convince yourself of this, you'll see that the square root of x squared is just a fancy way of writing the absolute value of x. Let's think about it. If you plug in 2, 2 squared is 4, square root of 4 is 2. If you plug in negative 2, that is 4, square root of 4 is 2. So whether you plug in 2 or negative 2, you end up getting 2 back, which is basically like absolute value. So if we were to graph this, we would see that this is an absolute value function shifted up 1 unit. And so we see that at x equals 0, which is right in between negative 1 and 1, there is a sharp corner. So mean value theorem does not apply because f of x is not differentiable at x equals 0. All right, here we have a piecewise function. And so if we sketch this, we will see, well, if I plug in 1 into the function here, I'll get 1 comma 4. If I plug in 1 here, I'll get 1 comma 3. And so this should actually say greater than or equal to 1. So that's a little typo there. So this is a cubing function. And so it's going to look a little bit like this, open circle. Here is a parabola that starts at over 1 up 3, and it's an up parabola here. So we can see that the function is not continuous at x equals 1. So you'll say mean value theorem does not apply because f of x is not continuous at x equals 1. Example 2, show that the conditions of Rolle's theorem are met for x squared minus x minus 6 between negative 2 and 3. All right, so first thing, once again, we have to prove that, number 1, that this is a continuous function. So you can say all polynomials, by definition, are continuous. Think about it. Linear functions, squaring functions, cubing functions are all continuous. All right, we know this is a parabola, so it's differentiable at all points. And Rolle's theorem basically says that f of A must equal f of B. Hence, when you connect these 2 points, you get a slope of 0. So we have to prove that before we can even use Rolle's theorem. So f of negative 2, see what we get. Negative 2 squared is 4, minus a minus 2, which is really adding 2. That's 6 minus 6, that's 0. F of 3 is going to be 3 squared, that's 9, minus 3 minus 6, so 6 minus 6 is 0. Well, f of negative 2 equals f of 3. So we know that there's got to be some point between negative 2 and 3 where the slope of this function is equal to 0 because the slope between these 2 points is 0. If we connect them, so f prime of x is 2x minus 1. And we want to set that equal to 0, which is the slope between these 2 points. So we'll get x equals 1/2. And so if we were to graph this on our calculator, you would find that at x equals 1/2, that you would have a slope of 0 on the curve. Example 3, we have the function 3 minus 5 over x on the interval 1, 5. And we have the graph over here. Visually, what is the mean value theorem trying to find? Draw it in. All right, so let's just say that we have the point 1. And if we plug in 1 here, we're going to get 3 minus 5 over 1. 3 minus 5 is negative 2. We can see that from the graph. So I'm going to go ahead and put that point right here on our graph. And then 5 is 3 minus 5 over 5. 5 over 5 is 1. 3 minus 1 is 2. We can also see that point right here. So if we connect these 2 points, all right, essentially what we're saying is there's got to be some point between 1 and 5. Maybe that point is over here somewhere on the graph, where the tangent line slope is equal to the slope between these 2 points. So that's what the mean value theorem is trying to find. It's trying to find this point C. So let's see if we can find that. All right. First, we need to find the slope. So f of b minus f of a over b minus a. So once again, we have our ordered pairs 1, negative 2 and 5, 2. So we're going to do 2 minus a minus 2, which is 4. And then 5 minus 1, which is 4. So that's 1. So looks like up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. So that makes sense. And now we have to take the derivative of this to find out where the derivative is equal to a slope of 1. So let's go ahead and do that. The derivative of 3 is gone. So f prime of x. And I'm going to go ahead and rewrite this as, well, I'll tell you what, I'll rewrite it as 3 minus 5x to the negative 1. I'm going to bring this x up. So the derivative, I should actually write it this way, the derivative is, well, that's gone, and we have negative 1 times negative 5 is 5x, and drop that power down, so 5 over x squared. And the question is, where is that slope equal to 1? So we're going to multiply both sides by x squared, and we end up getting x squared equals 5. So x equals root 5, which is approximately about 2.23. So let's see, 2.23. Yep, I'd say we got pretty close. Right, example 4, I like this practical example here. You're driving a car, you're traveling on an interstate highway at 50 miles per hour. You pass a police car. 4 minutes later, you pass a second police car, and you're traveling 50 miles per hour. No problem. The speed limit is 60. You're still going under the speed limit, right? The distance between the 2 police cars is 5 miles. Well, the patrolman in the second police car gives you a speeding ticket for driving 75 miles per hour. How can he prove that you were speeding? Wait a second. I was only going 50 miles per hour when I passed you. How did you know that I was going 75? Well, guess what? He can use the mean value theorem. Well, let's just take a look at it like this. speed, distance equals speed times time. So total distance that he travels, 5 miles. Okay, total distance. And the time, or should I say the time, is going to be 4 minutes. Now we have to convert that to hours. So 4 minutes times, there are 60 minutes in 1 hour. So 4 divided by 60 reduces to 1 over 15. Minutes cancel. So 4 minutes is equivalent to 1/15 of an hour. So 5 miles over 1 over 15 hours. Well, when we divide that fraction 5 over 1 times 15 over 1, we get 75 miles per hour. Meaning, in order for this person to go from point A to point B, 5 miles in 4 minutes, they had to have averaged a speed of 75. All right, which means they had to have gone faster than 75 in order to average 75, because they had to ramp up from 50 to get there and ramp down from 50 to get there. So we know that he was speeding. Now, you foolishly argue with the patrolman who is writing your speeding ticket. He calls his brother who's currently taking calculus and has just learned the mean value theorem. Bad news for you. Now the patrolman rewrites your ticket and charges you for driving 65 miles per hour twice during the 4 minutes. How can he prove this? Well, because if you average 75 and you were going 50, that means you had to go up to 75, or actually higher than 75. So that means at some point you were going 65. And then in order for you to pass the second patrolman at a speed of 50 miles per hour, that means you had to go down and get to the 50. Let's say this is 50, this is 50. And so on your way slowing down, you also were speeding again at 65 miles per hour. And by the way, which theorem is that? Oh, okay, that's the intermediate value theorem, which basically says you can't go from 50 to 75 without going through 65, and you can't slow down from 75 down to 50 without going through 65. Example 5, state whether the inverse cosine satisfies the hypotheses of the mean value theorem on the given interval of -1 to 1. Well, is it continuous? Yes, it is. Is it differentiable at all points in its interior? Not necessarily at the endpoints, so go back and read the definition there. Note, the derivative does not need to exist on the endpoints, but only on all points in the interior, which it does, so we can use the mean value theorem to find the point that has the same slope as the points in between here. All right, so let's first plug in our endpoints. So f of 1 is going to be the inverse cosine of 1. So what angle on the unit circle has an x value of 1? Well, that's going to be 0 radians. And then f of -1 is going to be, well, the inverse cosine of -1. So now we're thinking, what angle on the unit circle has a cosine or an x value of -1? Well, that's going to be pi. So now we're going to essentially do our f of 1 minus our f of -1 over 1 minus a -1. So f of 1 is 0 minus pi over 2. So our slope, and let me draw this in here so that you can really see it. Our slope between these points is essentially negative pi over 2. So that's my m, negative pi over 2. So what we want to do is we want to take this derivative and we want to set it equal to this slope of this red line that I drew to figure out where, at what points, is the slope going to have, is the derivative going to have that same slope? Well, it's going to be one there in green, and it's going to be another point over here in blue. Has the same slope. So let's see if we can find that. We're going to take the derivative of this. Well, we remember the derivative to be -1 over the square root of 1 minus x squared. Pretty simple. And we're going to set that equal to negative pi over 2. We're going to multiply both sides by negative, so essentially that gets rid of those. And then we're going to square both sides to get rid of this square root. So I'm going to go ahead and square both sides. When I square 1, I just get 1. When I square the square root, I get 1 minus x squared. When I square pi, I get pi squared. When I square 2, I get 4. I'm going to cross multiply here. And it's going to give me pi squared minus pi squared x squared equals 4. And then I'm going to move the pi squared over, so I'm going to have negative pi squared x squared equals 4 minus pi squared. And then I'm going to divide by negative pi squared, divide by negative pi squared, divide by negative pi squared. So I'm going to get x squared is equal to negative 4 over pi squared, because the negative doesn't matter. And a negative over negative is a positive 1. And then I'm going to take the square root, and my final answer is going to be x is equal to plus or minus, don't forget, negative 4 over pi squared plus 1. And those are the 2 points on the curve where the slope of the tangent line equals the slope between the points. For the sake of time, we are going to skip past example 6 because this is just a calculator version of all the other problems that we have done. You can look at those on the PDF on the website. All right, in example 7, we are going to learn how to determine when a function is increasing or decreasing. All right, essentially a function is increasing. Okay, if we could just kind of draw this out here. I'm going to draw some arbitrary function. And let's just say it looks like that. Well, this function is increasing when it has tangent lines that have positive slope. And notice it's decreasing now because the tangent lines have negative slope, and then it's increasing again here. So basically, when the derivative is positive, the function is increasing. When the derivative is negative, the original function is decreasing. So that's what we need to do here. So we're going to take the derivative, and so f prime of x is equal to 3x squared minus 12. What we want to do is we want to set that equal to 0 to find our critical points, because that's going to tell us when the function's derivative is 0, which means on one side it's going to be negative and on the other side it's going to be positive usually. So 3x squared equals 12. X squared equals 4, x equals plus or minus 2. All right, so now what we're going to do is we're going to make a number line. And on this number line, we're going to put negative 2 and positive 2. And we're going to plug in a number in each region, but we're not going to plug it into the original function. We're going to plug it into the derivative because we're trying to check what is the function's slope. So I'm going to plug in a number bigger than 2, like 5. Well, 5 squared is 25 times 3 is 75 minus 12. That's a positive number. Not important to actually get the number, but we just need to know if it's positive or negative. I'm going to plug in 0. Plug in 0 into the derivative, I get negative 12. Well, that's a negative. And if I plug in something smaller than negative 2, I'm also going to get a positive number. So that means the function is increasing, and then decreasing, and then increasing. So you'll say, in interval notation, it's increasing from negative infinity to negative 2 in union with 2 to infinity. And then you'll say it's decreasing from negative 2 to positive 2. All right, let's see if we can do this same problem over here in letter B. We have f prime of x is equal to, we're going to have to use the chain rule, 2/3. X squared minus 9, subtract 1 from this power gives you negative 1/3. And then we're going to multiply by the derivative of x squared minus 9, which is 2x. And so this is going to give us a 4x over 3 times the cube root of x squared minus 9. And this is our derivative. So what we need to do is we need to find our critical points. Once again, our critical points are where the derivative is 0 and where the derivative is undefined. So the derivative is 0 at 0. That's what makes the top 0. And the derivative is also undefined when x is 3 and when x is negative 3. So we're going to make a number line here, and we're going to put those critical points on our number line. So we have negative 3, we have 0, and we have positive 3. If I plug in a number bigger than 3, like 5, well, the top's going to be positive, the bottom is going to be positive, so that's positive. If I plug in a number like 1, well, the top is going to be positive, and the bottom, well, the bottom is going to be undefined. Excuse me, it's not going to be undefined because this is a cube root and not a square root. And you can take the cube root of negative numbers. So if you plug in 1, you get 1 minus 9, which is negative 8. The cube root of that is negative 2. So basically this is going to be negative. You plug in a negative 1, that's going to be a negative over negative. That's a positive. And this is going to be a negative. So you can go ahead and write the intervals out. It's going to be decreasing from negative infinity to negative 3 in union with 0 to 3. It's going to increase from negative 3 to 0 in union with 3 to infinity. Okay, last example here. We want to do something that's called antidifferentiation, which is basically going to lead us into the idea of an integral. And let's say we are told that f prime of x, the derivative of some function, is 2x minus 1. The question is, what could f of x be? Well, you have to think backwards now. That's why it's called antidifferentiation. So think about what could f of x be? Well, you'd have to think what would you be able to take the derivative of to get 2x? Well, that would have to be x squared, right? The derivative of x squared is 2x. And what derivative will give you negative 1? Well, that have to be negative x. However, you have to also put a plus c here. Some constant, because it could be x squared minus x plus 2, it could be x squared minus x plus 5, it could be x squared minus x plus 20, because when you take the derivative of this constant, it goes away and you're still left with 2x minus 1. So you have to account for the fact that this c could be anything. However, suppose you were told f of 2 equals 5. Well, now we can find out what this c is. So y is 5, 2 squared is 4, minus 2 plus c, so 5 equals 2 plus c. c equals 3, so therefore f of x must be x squared minus x plus 3. And so when you have initial condition, you're able to find out exactly what the original function is.